contender. Okay? We will do closed loop DPCM. Closed loop means what? We do prediction on the reconstruction with the head. Okay? That will make sure that our encoder decoder are not out of sync. There will be no accumulation error. Okay? So that is always the case. And then we usually employ block translation motion model. So basically searching for translational motion only. Okay? We're going to come back to that, and I'll try to explain why. Okay? Why is that the case? We talk about rotation, handing, all kind of different motion. How come we only worry about translation? Okay? The key is in the fact that you have 24 frames per second. So it's very fine. There's a really fine sampling rate in time, and typically object cannot move that fast. So it's hard to rotate 90 degrees in 1/24 of a second or 1/30 of a second. You typically do this, right? So that will take some time. And so with that fine sampling rate, most of the time motion turns out to be translation. Okay? So all international video coding standards are actually based on this coding framework right here. Okay, they all look like this with small details. Okay, the difference between them is actually very small. The improvement, but not a significant jump of any kind. So we have video teleconferencing guys like H.261, 263, 263 plus, 263 plus plus. And then finally H.264, which is the latest guy right now. And then so this with teleconferencing in mind, real-time communication in mind, okay? If you just want archive and playback, meaning storage and then playback at a later time, we have the MPEG series, like MPEG 1 in VCDs, MPEG 2 in DVDs, MPEG 4 in DivX, okay? So, a typical motion compensated codec will look like this. This is the input as a frame. So frame 1 coming in, frame 2 coming in, frame 3 coming in, so on and so forth. Now, you will do motion estimation based on a frame delay. Frame delay means the previous frame. Okay? Okay, so you delay the entire frame, and you take that delay frame, you do motion estimation with the incoming frame. Okay? This delay frame comes from inverse quantizer, inverse transform, inverse entropy coding. Means what? We do it on the head. We do it on the head. This frame delay has the head, the reconstruction, not the previous frame that you see over here. Okay, so we do it on the head. This is why this is called a closed loop codec. Okay, we do motion estimation. The result of the motion estimation will be fed into the motion compensation part. This motion compensation try to reconstruct, okay, the frames, and you take the difference. Okay, so this is the reconstruction with motion taken away already. Okay, and then you do a straightforward frame difference, and then the residue coming out right here will be fed to the straightforward transform quantization entropy coding, which is very similar to a typical image codec. Okay, so this is it. All right. Now this is the encoder, and if you want the encoder, as I said yesterday, the encoder has everything. When we do DPCM, closed loop DPCM, the encoder has everything. So at the encoder, you can display the reconstruction if you really want to. Okay, you can monitor the quality if you really want to. Okay, you can just tap it right here and then show it on your monitor. Okay. Another thing that we have to encode, not only the residue, but we also have to encode this. When we do motion estimations, there will be motion vectors. Okay, basically all the information, the psi information about the motion, that has to be encoded as well. So this arrow plus this arrow will comprise your total bit stream, your video bit stream. Okay, this doesn't go into the bit stream, right? This is for display only. If we want this to go to the bit stream, it will double your bandwidth immediately. Now, so the decoder is here. If you want to decode, take this part, okay, put it over there on the other end, and you're done. So typically, if you have the video encoder designed and implemented, the video decoder is 350. Okay? Now, let's talk about motion estimation. So formally, the goal of motion estimation is to extract the correlation between adjacent video frames. Okay? So these are my video frames, this is my time axis, and the general problem statement can be posed like this. Given the current frame C, say the one in the middle right here, current frame C, and the reference frame R, say the previous one right here, okay? Find the function fxy and gxy, where xy are the index of the pixels, okay? These xy are pixel index, okay? So find fxy, or transformation of pixel index, such that the distortion between the current frame and the reference frame being compensated like this is minimum. Okay? Now, there are many different ways. There are so many different functions that you can take for f and g. Okay? But the translation model means fxy is equal to x minus dx, and gxy is equal to y minus dy. dx, okay, so basically this is telling you that the object is moving away in the x dimension by this much, and it's moving away in the y dimension by this much. Okay? So moving, okay, if you just move sideways like this, then maybe this guy is 0 and this guy is 2. Okay? So it can move sideways, up, down in a translation fashion. Okay? So this is a very special case, the simplest case that we can think of for fxy and gxy. Now, if we just take the frame difference, okay? What is f and g? fxy equal to, if I just want to take the frame difference, I don't do any motion estimation. What is fxy? fxy is equal to, is that 0? Right? You don't move anything. Agree? So let's think about it a little bit. If I don't do any motion estimation, I just do frame difference, okay? Then fxy is just x, and gxy is just y. I'm not modifying the index. Every index stays exactly where it is, okay? Now, if I'm moving the index, that means I'm moving my object around, okay? So that's very important. And if I assume that this translational motion, and I do this operation on a block by block basis, okay, small block at a time, then what I have is a block-based motion estimation, motion compensation framework. So it's called BME for block motion estimations, and BMC for block motion compensation. Okay. Now, if it's not that clear, okay, let me move. Okay. Come back to that block motion estimation, motion compensation in a few minutes. So hopefully it will be clear. Let me say a few more terms that I will use throughout. Whenever I say inter means I'm going to look across. Okay? So intercoding means I will do coding with some kind of reference to the